Okay, this is the pre-lab video for experiment 3, mapping electric field lines. And here is the apparatus that you're going to be using. The idea is that the heart of this experiment is some conductive paper, or partially conductive paper. And this paper it looks just like normal paper, but it's partly coated with some conductive material so that it has some resistance per unit length. And so this is the paper we're going to be using because it acts just like a partial conductive object. And so the paper gets mounted on this corkboard, and what we want to do is set up different geometries of electrodes and then map the electric field lines of those geometries of electrodes. The first geometry you're going to set up is a capacitor geometry, so two parallel plate capacitor. So you want to set up a geometry like this, and these conductors will put all these spots on this piece of paper at the same potential and all these spots at the same potential, and then we'll be able to visualize the electric fields between these two different potentials by measuring voltages and whatnot with the multimeter. So the first step to do is to find your piece of paper that has the corresponding holes for the capacitor geometry. And so you'll do that. You'll have two pieces of paper. One of them will have these holes in this pattern, and the other one will have holes in a different pattern. So find the correct one. Each one of you will be given a pattern which is slightly different in this experiment. So some of you will have the spacing between the plates different than other members in your group. Each of you will have the spacing different than other members in your group. And so you place these copper electrodes on top, but now we have to make a good electrical connection between the electrodes and the paper, and that's what's in this little baggie of goodies for you. You have a bunch of thumb screws, steel thumb screws, and a couple of brass screws. So the idea is to use two of the steel thumb screws and one of the brass screws. And I'll tell you why. The brass screw has much better conductivity, electrical conductivity, than does the steel screw. Partly because these steel screws are a bit oily and whatnot. So anyway, these guys get tightened on, not super tight, but just, snug. And you would attach this one and attach this one. And then what you need to do is attach to create a potential difference between these two electrodes, and for that you'll use your DC power supply. And when you attach your DC power supply to these electrodes, you want to put this whole electrode at some potential, and you want to hook up by attaching to the brass screw. Right? It's important that you attach to the brass screw. It has better electrical conductivity than does the steel screw. And of course it's impossible to attach directly to the copper. So that's our attaching point. Okay, the exercises are then to measure the electrical potential difference between one of your electrodes and different spots on the paper. And for that you'll use your digital multimeter. For that you use the digital multimeter and the loose probes. So your digital multimeter, as usual, is tucked up behind the oscilloscope, and you would just touch this guy to the paper, to the electrode that you want to reference to, and then touch it to the paper. And of course, you should think about whether you're measuring DC or AC voltage. What's the correct way to do this? And another thing is you don't want to jab these probes into the paper because you'll create tears in the paper, and creating a tear in the paper effectively changes the electrical geometry of what you're doing. So you want to be careful to just rest this on the surface and not jab it in. Right? Tears will change what's happening here. And you'll be, you're explained in the lab manual what it is you're doing, but then you'll be using a pencil to mark different locations on the paper. The second part of the investigation, when you're still dealing with the capacitor geometry, is to try and measure the direction in which you have the maximum potential difference. the maximum voltage difference. And for that, you're going to use the probes. You'll have a second set of probes that are fixed together. And these guys are fixed together with tape. And the idea will be, you'll sit at some location, let's say the black is our reference end. You'll sit the black end of the probe at some location, and you'll wander around the red end of the probe. You'll wander around the red end of the probe and find the direction in which you have a maximum potential difference. And if you read the manual carefully, that's related to something. And it's related to, well, it's related to the electric field somehow, which you're going to be investigating. So you use one end of the probe as a reference, and you swing the other end around until you find a maximum voltage reading on your multimeter, and that will tell you something fundamental about electric fields. That's the first part of the experiment, is using the parallel plate capacitor geometry. The second part is using what we're calling a point charge with a question mark. And it'll be up to you to understand what we mean by that by the end of the lab. So once you complete part one, you'll have this paper marked up with pencil marks and whatnot. You'll write your name on it, and this will get submitted to the TA at the end of the session. You might want to snap a picture of this with your camera so you can refer to it at home if you need to. Okay, the second part of the experiment uses your second piece of paper. And this is a piece of paper with a central hole and a bunch of 6 holes around in a circle. So it corresponds to this hole and the holes around here. So it gets placed onto the corkboard. In the center, the idea is this is going to represent, well, we're introducing it as a point charge. And so the point charge is going to be this little round electrode in the center. And what we want to do is have this electrode at some charge. And so we'll attach it with a brass thumb screw, or a brass screw, because brass is the correct screw for making a good electrical connection, and if we used a steel one here, we wouldn't be able to make a good connection. Then, this is a point charge that's going to be put at some potential, so we'll attach a power supply to it, but somewhere we need to have our reference potential. Somewhere we need to define our V equals 0 location. And normally that's taken at infinity. It's assumed to be at infinity, but you'll see, you know, if your paper was infinitely big, you'd interrupt your neighbor and everyone else in the universe. So what we're going to do is use what's called a guard ring, and that's going to go around this, and it's going to get screwed on to the holes that are available, all 6 spots. And again, you'll use these steel thumb screws because they're a bit easier to work with, and actually quite a bit cheaper than the brass. And you'll use one brass screw. Right, and the one brass screw will be the place where you make your electrical connection, and the steel thumb screws you'll just sort of snug up so everything's tight. And you have to make sure to put in all these thumb screws. Right, if this ring is not pushed down flat and even, you're not going to have the geometry that you think that you have. Right, if I don't actually put these screws in over here, this side of the ring won't be well connected, and my field lines and my electric potentials will be disturbed. And again, you'll follow through the lab manual and take measurements of potential differences and draw electric field lines, and you'll actually use this geometry to investigate. There's some exercises where you'll investigate Gauss's law using this geometry. And so I think that's enough to get you going in terms of the technical side of things, and the rest of the information you'll see when you get here and you'll read in the lab manual. Good luck.